Hello everyone, welcome to Maths Smart Tips. In this video, we are discussing the homogeneous linear equations with constant coefficient of partial differential equation section. And in the previous videos of partial differential equations, I already discussed different topics on partial differential equations with some great examples. So those who are new, those who are not watching the videos, I will share the link in the description and also here in the I tab. So you can check the link for the videos on partial differential equations. Partial differential equations is an important topic for any higher math exams. So, and this topic, homogeneous linear equations, the solution procedure of homogeneous linear equations is also a very important topic. So let's start, and before starting the solution, I am requesting you to all those who are new in my channel, please like the video, comment if you have any doubt in the comment section below, and don't forget to subscribe the channel. So an equation of the form a0 del nz del x power n a1 del nz del xn del y plus dot plus an del nz del yn equal to fxy, where ai's are the constant, are called the homogeneous linear PDE with nth order with the coefficient with constant coefficient. It is called homogeneous because all terms contains derivative of same order. Now it can be also written as phi of d dash of z is equal to fxy, where the capital D stands for del x and capital D dash stands for del y. Now before going to solution, two important points, which one is complementary function and second one is particular integral. We all know that for differential equation with constant coefficient, to write the complete solution we need these 2 points, that is CF complementary function and particular integral, and the complete integral equal to y equal to CF plus pi for an ordinary differential equation. Here in case of partial differential equation, the process is also same. So the complementary function is the complete solution of the equation phi of d dash of z, this is equal to 0. It must contain n arbitrary functions where n is and the order of the partial differential equations, and the particular integral is a particular solution of phi d dash of z, this is equal to fxy, and the complete solution is z equal to cf plus pi, since here z is the dependent variable on the variables x and y. This gives the complete integral. Now method of finding complementary function of the PD. The first one is this term operating on z, this is equal to fxy, this is the equation, and the CF, that is complementary function of the general solution of this right side. If we take 0, that is homogeneous equation, then we get and put d equal to m and d dash equal to 1 in the equation 2 to get this type of equation a0 m power n plus a1 m power n minus 1. So this is an nth degree equation in m. So we find m roots of these equations now. So n roots for the equation. So let m1, m2, mn be the distinct roots of the equation 3. Then the complementary function is phi 1 y plus m1x, phi 2 y plus m2x plus dot plus phi n y plus mnx. And if the root m be repeated 8 times, then the complementary function is, as we see in ODE section, this is the concept here also same, that is phi 1 y plus mx plus x, phi 2 y plus mx plus x square, phi 3 y plus mx plus dot plus x power r minus 1 phi r y plus mx. This is same as we do in ODE section. Now let us take an example first. Solve this equation, this d square plus 5 d dash plus 2 d dash square z equal to 0. Since here the right hand side term is 0, so the complementary function gives the complete integral for this complete solution for this equation. So the auxiliary equations are 2m square plus 5m plus 2. If we put d equal to m and d dash equal to 1, then this gives these equations, and this gives the root m equal to minus half and minus 2, which are two distinct roots. Therefore the solution is phi 1 y plus m1x, that is this is the m1, and phi 2 y plus m2x, this is m2. So this gives the solution, general solution. Let us take another example, example 2. D square plus d dash square plus 2 d dash of z, this is equal to 0. and this gives the root -1 which is the w. That means the root -1 repeated 2 times, that is this is the root of multiplicity 2. Therefore the general solution is phi 1 y minus mx y plus mx, that means m equal to -1, so y minus x plus x phi 2 y minus x. This is the solution for the repeated root case. Now let us take another example. So the example is d to the power 4 plus d dash square minus 2 d square d dash square, this operating on z, this is equal to 0. Sorry, this should be power 4. So if we take this, then this gives m square minus 1 whole square, and the roots are m equal to 1 1 minus 1 minus 1, that is 1 is a root of multiplicity 2 and -1 is a root of multiplicity 2. Therefore in this case we write the general solution and as in the form z equal to phi 1 y plus mx, that is phi 1 for the root 1. So these two terms for the root 1, phi 1 y plus x phi 2 y plus x, and these two terms for the root -1, that is phi 3 y minus x plus x phi 4 y minus x. Now this is the method to find the complementary function. Now we find the particular integral. Now method to find the particular integral, method number 1, depend upon the functions on the right hand side. So if the functions, that is these functions, which function, this fxy function depend on these functions fxy, different types of PDE are different types of particular integrals occurs. So the type 1 is when fxy equal to e to the power ax plus by, particular integral equal to 1 by dd dash, this is the this operator term phi of dd dash of e to the power ax plus by, which is equal to phi of ab e to the power ax plus by. Put d equal to a and d dash equal to b, provided phi ab not equal to 0. Now if in the case if we put a, the value of a and b, and we get the denominator term 0, that means phi ab equal to 0, then what we shall do, we will do particular integral, we differentiate with respect to d and multiplied by x, or we should differentiate by d dash and multiplied by y, and then this operate on this function e to the power ax plus by. Now if in case this term is again 0, then we should, what we should do, we should do again multiplied by x, and the order of the partial differentiation should be higher, that is 2. So in this case, and put the value of ab, then we get the value of this particular integral for the function e to the power ax plus by. And in case here also same procedure, and this process we can continue whenever this denominator term not equal to 0. You should continue this process not equal to 0. So now let us take an example. Find the particular integral dq minus 3 d square d dash plus 4 d dash q operate on z, this is equal to e to the power x plus 2y. Now comparing with this function e to the power ax plus by, this gives a equal to 1 and b equal to 2. So particular integral equal to dq minus 3d square d dash plus 4 dq. This is a function of d and d dash, that is phi of d and d dash. This is equal to dq minus 3d square d dash plus 4 dq operating on this function. Now we first calculate the phi of 1 2, that means for a equal to 1 and b equal to 2, we find phi 1 2, which is we get 27, which is not equal to 0. Therefore this gives the particular integral, since this term is not equal to 0. So the particular integral equal to 1 by 27 e to the power x plus 2y. Now let us take another example. D square minus 2 dd dash plus d dash square of z is equal to e to the power ax plus by. So here a equal to 1 and b equal to 2, and the denominator term of this is equal to phi d dash equal to d square minus 2 d dash plus d dash square this, and phi 1 1 equal to 0. So what we should do, we should do differentiate this with respect to d or d dash and multiplied by x or y, and continue this process whenever the denominator term at the point a and b not equal to 0 occurs. So del phi del d equal to 2d minus 2d dash this, and del phi del d at 1 1, this gives also 0. So this we should increase the order of the derivative. So del phi del 2 phi del d2, this is equal to 2, and if we put the point, then this gives 2, which is not equal to 0. So del 2 phi del d2 not equal to 0. That means the particular integral should be x square by del 2 phi del d2 at the point 1 1 of this function. This is equal to x square by 2 in x to the power x plus y. Similarly, if we do the derivative with respect to d dash, then we get del phi del d dash equal to this at the point 1 1. This gives also 0. Say so we should increase the order of the derivative. So del 2 phi del d dash square, this is equal to 2, and at the point 1 1 is not equal to 0, that is 2, and particular integral is equal to y square del 2 phi del d2 at the point 1 1, and this is the function. So this gives y square by 2 it is bar x plus y. So these two are the possible particular integrals for the above differential equation, partial differential equation. Now we go to the next type. The type 2 is when the function fxy equal to x power p y power q forms. Pq belongs to integer. So particular integral equal to 1 by phi d dash d dash x power p y power q. So we expand, this is an inverse function, so phi of d d dash inverse x power p y power q. Now expand this phi of d d dash inverse in powers of d by d dash if it is p less than q, and expand this inverse phi of d d dash in powers of d dash by d if p greater than q. When p equal to q, you should try both the expansion, whether which expansion is easy, you should apply this expansion, those expansions. Also we have 1 by d fxy is equal to fxy into dx, taking y as constant, and in case of d dash, integration fxy dy, taking x as constant. Now let us take an example. Particular integral of d square plus d dash minus 6 d dash square of z, this is equal to x plus y. Here if we take p and q, so p and q are 1 and 1. So pi equal to 1 by d square plus d dash minus 6 d dash square. Now if we take common d square, then this that remaining term is functions of d dash by d. So we now expand this function 1 plus this function in terms of d dash by d. So this is the expansion of the form 1 plus x inverse, and this is equal to 1 plus x square plus and so on, sorry, 1 minus x square plus x square alternative minus plus minus and so on. So this is the complete x term. So this gives 1 by d square into 1 minus first term, and since the power of the function is linear, so we do not write the higher order derivative terms or higher terms of these functions, since this will be vanished after first derivative terms. So 1 by d square into operate on first 1, so 1 means this is identity, sorry, this is identity, so this gives x plus y, and then it should be operate on this, so 1 minus 1 by d into d dash of x plus y, and d dash of x plus y means d dash of x plus y means d dash means what, del y of x plus y, and this gives simply 1. So this is the 1, and if 1 by d means integration with respect to x, taking y as a constant, so this integration of dx, this gives simply x. So this gives x plus y minus x, x cancel out, and 1 by d square into y, and then integrating with respect to x of this function, taking y as a constant 2 times, in this is d square, 1 by d into 1 times integration, then again 2 times integration gives y x square by 2. So this is the particular integral for the above differential equation, this partial differential equation. Now let us come to the next types of problem. When the function fxy is of the form sin ax plus by or cos ax plus by, then particular integral 1 by phi d square d dash and d dash square sin of ax plus by, this we replace d square by minus a square, d dash by minus ab, and d dash square by minus of b square of this function sin of ax plus by, provided phi of this is not equal to 0. When phi equal to phi of this equal to 0, then we apply the same process as we discussed above. Which process? The process is this one. Derivative with respect to d multiplied by x, this process, the same process we apply here also, if the denominator term should be 0. So let us take an example. let us take d square minus 3 dt dash plus 2 d dash square on z. This is equal to cos of x plus 2y. This is equal to 1 by d square minus this of x plus 2y. Here a equal to 1, b equal to 2, since this is of the form ax plus by. This is a equal to 1 and b equal to 2. So now we replace d square by minus a square, dt dash by minus ab, and d dash square means minus b square. That means this is minus 1 square. This should be replaced by minus 1 into 2, and this should be replaced by minus of 2 square. So this gives the denominator. In the denominator the coefficient is minus 1 by 3, which is 3, which is not equal to 0. That means this minus 1 by 3 cos of x plus 2y is the particular integral for the above equation. Now if we find the complementary function, so this is the auxiliary equation. This gives the two distinct roots, 2 and 1. So complementary function is phi 1 y plus m1x and y plus mx, that is phi y plus 2x and y plus x. So complete solution is y equal to cf z equal to cf plus py. So this is equal to z equal to phi 1 y plus this, and the particular integral is minus 1 by 3 cos of x plus 2y. Now let us come to the next type 4. If fxy equal to v of x plus y, it is for ax plus by. So particular integral equal to 1 by phi of d dash v of xy e power ax plus by. This is equal to e power ax plus by. Phi d should be replaced by d plus a, and d dash should be replaced by d dash plus b, and operate on this function v of xy. Now let us come to the next type problem. Whether fxy equal to any function, that is any arbitrary function, then the procedure is first resolve phi of dd dash into partial fractions, then consider phi of dd dash as a function of d alone. Particular integral equal to 1 by d minus m d dash. This m is the root of the complementary function, or root of the auxiliary equation, on dd dash into fxy. This is equal to f of c minus mx into dx. C should be replaced by y plus mx after integration. So first we replace y by c minus mx, and then after integration c should be replaced by y plus mx. Now let us take the example d square plus d dash minus 6 d dash square of z. This is equal to y cos x. First we find the auxiliary equation m square plus m minus 6, that is put d equal to m and d dash equal to 1. We get this auxiliary equation, and if we find the root, then m equal to minus 3 and 2 are the two roots. So complementary function is y plus 2x and y minus 3x. Now particular, so roots are these two. The particular integral equal to 1 by d square plus d dash minus 6 d dash square of y cos x. This is equal to partial fraction 1 by d plus 3 d dash d minus 2 d dash of this y plus y cos x. So if we operate first this function, first this operator, so d 1 by d plus 3 d dash rest, and d plus minus 2 d dash operating on this function. So d minus 2 d dash, so we have to consider this phi of d dash as a function of d alone. So this means this is the integration c minus 2x where y equal to c minus 2x cos x dx. This is the integration of this function. You can check this process. So this is the integration, simple integration, and after integration we should replace c minus 2x by this y. So this is the first, for the first case. Now for this operator we again consider this function as a function of d alone and operate this function. So c plus 3x into sin x, c plus 3x instead of y equal to c plus 3x and minus 2 cos x. If we integrate this, then we get, at last you can check the calculations, sin x minus y cos x. This is the particular integral for the above PDE. So the complete solution is y equal to cf plus py. So this is the complete integral for the above equation. So this is the content for this video. If the content is helpful, then please give a like to this video, share with your friends, and subscribe the channel. Thank you friends. See you again in the next video.